Using heuristics, we closed the previous section by briefly discussing ways in which the size of a search tree can be controlled through the use of elementary techniques. In this section, we look at this problem in more detail and discover that the equivalent of intuition can be added to our system to increase efficiency. We might begin by considering how we as humans would proceed when faced with the 8 puzzle. We would rarely pursue several options at the same time as our previous control system did. Instead, we probably would select the option that appeared most promising and follow it. Note that we said appeared most promising. After all, we usually do not know for sure which option is best at a particular point but follow our intuition, which may, of course, lead us into a trap. Nonetheless, the use of such intuitive information seems to give humans an advantage over the brute force methods of selection. The previous section where each option was given equal attention. It is customary to refer to such untested and empirical information, which humans gain by the use of intuition, as heuristic information. More specifically, we define a heuristic policy as one that leads in a direction that appears to be the best, but offers no assurance that it will turn out to be the correct direction. Thus, whereas a human might follow a rule of thumb, we speak of a program applying a heuristic policy. Designing heuristics. The first step is to identify those characteristics for which we as humans look when deciding which option to pursue. In general, we can argue that humans tend to keep the goal state in mind and pick the option that appears to lead toward that state. In the case of the 8 puzzle, this means that a human, when given a choice, tends to select the option that moves a tile in the direction of its final position. To apply this technique in a programming environment, we must first develop a quantitative measure by which a program can determine which of several states is considered closest to the goal. Such a measure is called a heuristic. One heuristic might be to associate with each state the value equal to the number of tiles out of position and consider the state with the smallest value to be closest to the goal. However, this value does not take into account how far out of position the tiles are, so we might want to adopt a slightly more complicated measure that accounts for this distance as well. One technique is to measure the distance each tile is from its destination and add these values to obtain a single quantity. The distance in this case can be taken as the minimum number of moves a tile must make to reach its goal position, disregarding any complexities introduced by the location of the other tiles. Thus, a tile immediately adjacent to its final destination is associated with a distance of 1, whereas a tile whose corner touches the square of its final destination is associated with a distance of 2, because it must move at least one position vertically and another position horizontally. Adopting this system, we observe that the quantity associated with each state is actually an approximation of the number of moves required to reach the goal from that state, which we refer to as the projected cost. For instance, the total projected cost associated with the configuration in the current figure is 7 because tiles 2, 5, and 8 are each a distance from 1 from their final destinations, while tiles 3 and 6 are each a distance of 2 from home. In fact, it actually takes 7 moves to return this puzzle configuration to the solved configuration. The projected cost has 2 important characteristics. First, as just noted, it constitutes a reasonable estimate of the amount of work remaining in the solution if that state were reached. This means that it should be helpful in decision making. Second, it can be calculated easily. This means that its use has a chance of benefiting the search process rather than of becoming a burden. In contrast, although the actual number of moves required to reach the goal from the given state is an excellent piece of information to have when making decisions, computing this information involves finding the actual solution first. Applying heuristics. Now that we have a heuristic for the 8 puzzle, the next step is to incorporate it into our decision-making process. To this end, we recall that a human faced with a decision tends to select the option that appears closest to the goal. We then alter our search procedure of the previous section to consider the projected cost of each leaf node in the tree and pursue the search from a leaf node associated with the smallest such cost. Based on this principle, we present the algorithm in such figure for developing a search tree and executing the solution obtained. Establish the start node of the state graph as the root of the search tree and record its heuristic value. While the goal node has not been reached, do selected the leftmost leaf node with the smallest heuristic value of all leaf nodes. To this selected node, attached as children those nodes that can be reached by a single production. Record the heuristics of each of these new nodes next to the node in the search tree. Then, outside of the while loop, traverse the search tree from the goal node up to the root, pushing the production associated with each arc traversed onto a stack. Solve the original problem by executing the productions as they are popped off the stack. Let us walk through this algorithm as it applies to the 8 puzzle. Starting from the initial configuration. In the previous figure, we unsolved the 8 puzzle, where the 2-2 position is empty. First, we establish this initial state as the root node and record its projected cost, which is 5. Then the first pass through the body of the while structure instructs the addition of the 3 nodes like the following. Note that we have recorded in parentheses the projected cost of each leaf node beneath it. The goal node has not been reached, so we again pass through the body of the while structure, this time extending our search from the leftmost node, the leftmost leaf node with the smallest projected cost. After this, the search tree has taken the form displayed in the following figure. Note that the projected cost of the leftmost leaf node is now 5, indicating that this is perhaps not a good choice to pursue after all. The algorithm picks up on this, and in the next pass through the loop instructs us to expand the tree from the rightmost node, which now is the leftmost leaf node with the smallest projected cost. Having been expanded in this fashion, the search tree appeared as in the following figure. At this point, the algorithm seems to be on the right track. Because the projected cost of this last node is only 3, the while structure instructs us to continue pursuing this path, and the search finally arrives at the goal, with the search tree appearing as in this figure. Comparing this with the tree in the previous figure shows that even with the temporary wrong turn taken early on by the new algorithm, the use of heuristic information has greatly decreased the size of the search tree and produced a much more efficient process. After reaching the goal state, the while structure terminates, and we move on to traverse the tree from the goal node up to the root, pushing the productions encountered onto a stack as we go. The resultant stack appears as depicted earlier. Finally, we are instructed to execute these productions as they are popped from the stack. At this point, we would observe the puzzle-solving machine lower its finger and begin to move the tiles.